Hey calculus students, thanks for joining me today. So we've spent the last couple days looking at the mean value theorem. And I want you to remember for just a minute, what we did right before the mean value theorem is we were working on finding extrema, right? That we were looking to find where there might be a relative minimum, a relative maximum. And that's what we're going to go back today because remember, we've already learned how to take derivatives. What we're working on now is how derivatives help us, what their applications are. And we're going to learn something today that's going to help us find extrema called the first derivative test. But before we get to that first derivative test, let's just make some observations here and we'll kind of build up to what our first derivative test is going to tell us. So I have an interesting graph here up on my screen, and when I take a look at it, I really notice that there are kind of four distinct intervals to this graph, and let's make some observations of those. So I'm going to use a dashed line, vertical dashed line, to split it into the intervals that I see. Well, maybe if my pen allows me. There we go. There, and there. Okay. So what's different in each of these intervals? Well, when I take a look at the interval from here to there, what I notice is that the function is increasing in this interval. Now, when we think about the derivative, okay, remember that derivative is about slope. Okay, and what I notice here is that the slope of this curve is always positive in this interval. So I'm going to make the note here that f prime of x is greater than 0, that the slope is always positive in that interval. Now when I look at the interval here, this is constant, isn't it? Okay. And what's the slope of every point in this interval? That would be 0. Now on this interval, the function is decreasing. The slope is always negative. So decreasing, which means for every point in that interval, f prime of x is less than 0. And then back in this interval, the slope is always positive. The function is increasing. The derivative is always positive. The slope of every point there is positive. Now let's look at a few more graphs. Okay. Well, here I see changes from increasing to decreasing at all of those points, right? It goes from increasing to decreasing to increasing to decreasing to increasing. Okay. Here I see it change from increasing to decreasing right there. Okay. So as we take a look at these graphs that I've just showed you, how do I know when a function is increasing, decreasing, when it changes from increasing to decreasing? Well, look at the graph right here. It actually might be easier if I get rid of these vertical lines. Notice that the graph changes from increasing to decreasing right here. And what's special about that point right there? This point has a slope of 0. Okay, so f prime of x equals 0. Same right here. F prime of x equals 0. Now how about here? It changes from increasing to decreasing. Is f prime of x equal to 0 here? No, it's not. That's a sharp turn. It doesn't have a slope. Now at sharp turns, we've always said those are not differentiable. Okay, and right here, we're back to f prime of x equaling 0. So it changes from increasing to decreasing wherever the slope is equal to 0 or it's not differentiable. Now, if you recall, those are called the critical numbers or the critical values. Okay, so we see the critical values are important in helping us, okay, split into intervals of increasing and decreasing. Now, in this one, where does it change from increasing to decreasing? Well, there's this vertical asymptote right there, right? Now, The vertical asymptote is not a critical number, because for it to be a critical number, the point has to be defined. So we see it change from increasing to decreasing at a vertical asymptote at a value that is not in the domain. All right. Okay. Now that could also happen. I could have a graph like this, and it might have a hole here, and it could come down like this. So it changed from increasing to decreasing at a hole. So there was no critical point there. So it's also going to be important for us to identify values that are not in the domain. Okay. So how do we determine if a function is increasing or decreasing? Well, if f prime of x is greater than 0, the function is increasing, the slopes are positive. If f prime of x is less than 0, the slopes are negative, it's decreasing. If f prime of x equals 0, the slope is 0, the function is constant. So how do we find where a function is increasing or decreasing? Well, just like I talked about on this slide, we find critical numbers or values not in the domain. That's going to create intervals. Okay. Then what we do is we test f prime in each of those intervals to determine if f prime is positive, negative, or possibly 0 in between those critical numbers or values not in the domain. So let's look at an example. Find the open intervals for which a function is increasing and decreasing. Here's our function, x to the fourth minus 2x cubed. To find where it's increasing and decreasing, we first have to find the critical numbers or values not in the domain. Now, I'm going to make a note right here. Our domain is all real numbers, right? This is just a polynomial. So there aren't any of those values that we're going to have in here. But we're ready to find the critical numbers by taking the derivative. F prime of x, 4x cubed minus 6x squared. We need to set this equal to 0 and solve. I'm going to factor out a 2x squared. So I get x equals 0 or x equals 3 over 2. So these are our critical numbers. Okay. So the way I like to do this then is I like to draw a number line. It's kind of like the x-axis. Okay. And I put my critical numbers or values that aren't in the domain on this axis. So let's call this x equals 0. And let's say x equals 3/2 is right there. So I've split it into 3 intervals here. Okay. It's kind of like we're working the reverse on this one. Okay. We know where there's critical numbers. We don't know what the graph looks like between those. But if we can set those critical numbers or values not in the domain, we can then test the derivative, the first derivative in each of these intervals. Okay. Now, to the left of 0, okay, I could put in -1, -2, I could put in -100. It doesn't matter. This is a critical number. Okay. So the derivative here is either going to always be positive, always negative, or always 0. But it's not going to be always 0 because these are the only places where it's 0, right? So the derivative is either going to be always positive or always negative. So I can pick any value in this interval. Doesn't matter which one. I don't have to test more than one. Okay. So let's say I want to test f prime of -1. All I care about is it greater than 0 or is it less than 0? Okay. So let's go to f prime. And if I substitute -1, 4 times -1 cubed minus 6 times -1 squared. I'm going to make sure I don't goof this up here live on television. Okay. I got -10. But like I said, I don't care it's -10. All I care is that it's negative. Okay. At -1, okay, f prime is negative. At -2, it would be negative. At -100, it would be negative. It's going to be negative for every value in this interval. What does that tell us about the function in this interval? Well, it tells us if the slope is always negative, the function is decreasing. Okay, it's decreasing in that interval. Now let's go to the next interval, between 0 and 3 halves. I can pick any value I want and substitute it into the derivative. I'm going to pick 1. Okay, so I'm going to go to f prime. 4 times 1 cubed minus 6 times 1 squared. What do we end up with there? That's a negative. I don't need a calculator. That's just 4 minus 6. That is negative. So it's going to be negative for every value between 0 and 3 halves, which means our function is decreasing. Last interval, I just need to pick a value to the right of 3 halves. I'm just going to pick 2. 4 times 2 cubed minus 6 times 2 squared. I get positive number. I get positive 8. It's positive over here, so it's positive for every value. And if the derivative is positive, the function is increasing. So we found the critical numbers. We split it into intervals. We tested an interval, tested each interval by substituting one value into f prime to determine if the function is decreasing or increasing. So let's answer the question. Find the open intervals on which f of x is increasing and decreasing. It is decreasing on negative infinity to 0, exclusive, union 0 to 3 halves. Now, why can't I say just from negative infinity to 3 halves? Well, what was the value of the derivative at x equals 0? 0, right? It was a critical number. At 0, f prime is 0, so it's not decreasing at that point. It must have a horizontal tangent line. Maybe we can pull up the graph here in a minute just to confirm this. And then it is increasing on 3 halves to infinity. So now we know exactly where this function is increasing. We know exactly where it is decreasing. Okay, let's graph this just to confirm. X to the 4th minus 2x cubed. Here we go. Okay, does it match what we said? We said it's decreasing from negative infinity to x equals 0, and then from 0 to 3 halves. Yeah, that's exactly what we see. And look at what do we notice there? There's that horizontal tangent line, okay, where we come down, it's decreasing, the slope is 0, and then it decreases again, and then it increases after that. All right. Okay. So how does this help us find extrema? Because remember, that's what I kind of mentioned we're working on here, is we're working on finding extrema. Okay. Well, if we know where a function is increasing or decreasing, I think we can use that to help us determine if we have a maximum or a minimum. I think this will make sense to you. If f prime goes from negative to positive, okay, that means it goes from decreasing to increasing. Okay, right? A function goes from decreasing to increasing. Okay, that must be a minimum. Right? So it's just like this. Okay, function goes from decreasing to increasing. That's a relative minimum. Okay. If it goes from, f prime goes from positive to negative, that means it goes from increasing to decreasing. Must be a maximum. Now, if it does not change, if it's positive on both sides or negative on both sides, then it has neither. So remember that we find those critical numbers, and those critical numbers can be a maximum or minimum. Okay? So remember, if it's an extrema, then it's a critical number. Okay? Now, it doesn't mean if it's a critical number, then it's an extrema. If, in our last example, 0 is a critical number. Is 0 an extrema? No, because it goes from decreasing to decreasing. It stays the same. Look at our graph. It goes from decreasing to decreasing. This is not an extrema. However, over here, it goes from decreasing to increasing. So it's going down, then it comes up. So x equals 3 halves would have to be a relative minimum. Decreasing to increasing, look at the graph. Decreasing to increasing, this is a relative minimum. So this is our first derivative test, okay, that we can use intervals of increasing and decreasing to help us determine where the extrema are. And I just wanted to draw the last cases where it's neither a maximum nor a minimum. So find all extrema of this function. Now we are making a shift, okay? In the problems that we were doing before, we were working on a closed interval, so we had to include the endpoints, and that's still true. If you have a closed interval, you have to consider the endpoints. However, I didn't say what the interval is, so we're talking about extrema anywhere on the graph. And taking a look at this is a polynomial, and its domain is all real numbers, which is important for us, right? Because we know it can switch from increasing to decreasing at a vertical asymptote or a hole or something like that. So we have to consider the domain. But what are the extrema anywhere on this? So what do we have to do? We have to find critical numbers. Take our derivative. 3x squared plus 4x. Okay, we set it equal to 0 and we solve. I'm going to factor out an x. And we get x equals 0 or x equals negative 4/3. Are there any values where the derivative is undefined, okay, where it's not differentiable? No, the derivative is a quadratic. It exists at every value of x that's in the domain of our function. So these are our critical numbers. Okay. Now before, what we did is we just plugged 0 back in, we plugged negative 4/3 back in, and we use that to determine what the extrema are. Well, now let's set up that x-axis, that number line. Let's call that x equals negative 4/3. Okay, and x equals 0. Let's split it into intervals and determine where the function is increasing and decreasing. So let's test a value to the left of negative 4/3. Okay, and when I say test, that means we're putting it into f prime. So I'm thinking negative 2. Substitute negative 2 into f prime. 3 times negative 2 squared plus 4 times negative 2. I get positive 4. It's positive, so the function here is what? Increasing. Now I'm going to test the value between these two. I'm going to pick negative 1. F prime of negative 1. 3 times negative 1 squared plus 4 times negative 1. I get negative 1. So here it's negative. The function is decreasing. Lastly, let's pick a value to the right. I'm going to pick 1 and put it into f prime. 3 times 1 squared plus 4 times 1, that is positive. The function is increasing. So what do we have for extrema? Well, it goes from increasing to decreasing, going up to going down. So that means x equals negative 4/3 is a relative maximum. Increasing to decreasing, maximum. Then it goes from decreasing to increasing at 0, so x equals 0 is a relative minimum. Now, could one of these potentially be an absolute maximum or absolute minimum? Potentially. To do that, we would actually have to compare their y values. However, looking at this function, this is a cubic function. What's the end behavior look like? We know cubics kind of look like this. And that's what this function kind of looks like, right? It's increasing to decreasing to increasing. But I know this goes down to negative infinity, this goes up to positive infinity. So neither of these are going to be the absolute maximum. Let's look at one more. Find all extrema for x squared over x squared minus 9. So we need to start by considering the domain. It's all reals, but x cannot equal plus or minus 3. So it's going to be important when we create our x-axis, our number line here, that we put -3 and +3 on there. Because, well, and let's think about this. What do we have at plus or minus 3? Or is that a whole or is that a vertical asymptote? Well, at 3 and -3, the denominator is 0, but the numerator is not. Okay, and we know that those are vertical asymptotes. So I'm going to make a little note here. They're not wholes. Remember, wholes happen when you get 0 over 0, when a factor in the numerator cancels out a factor in the denominator. These are vertical asymptotes. And it's possible for a function to change from increasing to decreasing on opposite sides of a vertical asymptote. So these aren't critical numbers, but they are important for us as we find intervals of increasing and decreasing. Now let's find our critical numbers by taking a derivative. Little bottom d top action here. X squared minus bottom d top minus top d bottom over bottom squared. So that's 2x cubed minus 18x minus 2x cubed. Did I do that right? 2x cubed minus 18x minus... All right. Well, those 2x cubes are gone. So we just have negative 18x over x squared minus 9. Now, where is this equal to 0? Okay, I'm going to set this thing equal to 0. Well, we know a fraction's only equal to 0 where its numerator is equal to 0. Okay, which is at x equals 0. Now, are there any values that we can't put into the derivative? Well, looking at the derivative, I know x can't equal plus or minus 3. However, we already have those listed as values not in the domain. They're vertical asymptotes, so we don't have any additional points to add other than x equals 0, okay, is a critical number. So we have 4 intervals now that we need to test. Let's test the value to the left of -3. I'm thinking -4. Put that into the derivative. Now, one nice thing about quotients here is that you can save yourself a full substitution. If I look at the denominator here, it's being squared. So our denominator is always positive. So I really only have to look at the numerator. When I put in -4, the numerator is positive. So I have a positive over a positive, which is positive. The function is increasing. Now let's test between 0 and -3, like at -2. And again, I get a positive over a positive, which is a positive. The function's increasing. So we don't see a change. It goes from increasing on one side of a vertical asymptote to increasing on the other. What might that look like? Increasing to increasing. The vertical asymptote, the behavior might be like that. It's increasing on this side, and then on this side, it's increasing as well. So we don't see a change there. And -3 is not in the domain, can't be an extreme anyway. Now let's test the value to the right here, like 1. Well, now my numerator is negative, but my denominator is positive. A negative divided by a positive is negative, so the function's decreasing. So it changes from increasing to decreasing. I think we know what's going on at x equals 0. It goes from increasing to decreasing. This must be a max. On the other side of the vertical asymptote, okay, at 4, again, it's a negative divided by a positive, which is negative, so it's decreasing there as well. Okay. So as for extrema, x equals 0 is a relative max. Now, what would this graph look like? I already said there's a vertical asymptote at -3 and 3. Okay. So let's say this was -3, and then we've got 3 here, another vertical asymptote. And what happened? At 0, we had a maximum. It changed from increasing to decreasing. So I know it's actually going to come back down that way, right, and approach the vertical asymptote while decreasing. And then on the other side of the vertical asymptote, it also must be decreasing. So over here, it's got to be going down. So it probably needs to start up there and come down something like that. So what our next step is, in our next video, you're going to see that we're going to really start sketching what I'm going to say are the best graphs of your life. We have a couple more things. I have a rough idea of what this graph looks like, but you're going to learn a couple more things that's really going to zero in on some details that will help you make the best graphs of your life. But for now, first derivative test. Where are functions increasing, decreasing? How can you use that to find extrema? Thanks for watching. We'll see you later.